Okay, this is, I hope, the last part of Lecture 8. So that last example was really long and ugly and very difficult. The good news is you're not going to have to do stuff like that on an exam, but it is fair game for homework. Especially, it's good if you can do a problem like that and keep your sanity and know what it is that the problem was asking in the first place. So we'll do another difficult one, but let's take a break from the difficult ones and do an easy one. So what I want to do is actually calculate something that we now have the tools for doing. What I want to do is find an equation for the tangent line. So to understand this in the easiest way possible, let's look at an easy example where f of x is our old friend x squared. And I want to choose a point to find the tangent line at that might be somewhat interesting. Let's think of the graph, which looks like this, of course. And we'll pick a point, let's say, out here at x equals, let's say, -3. So this point would be x equals -3. So I want to know the equation of the tangent line. We can see what it looks like. It would look something like that, right? But what's the equation for the tangent line? Well, what do I need to do to get the equation? Well, anytime you're looking for an equation of a line, you need two things. You need the slope for sure, and you either need a y-intercept or you need a point. Most of the time, we're going to need a point like an A and a B, x and a y coordinate. So that's the plan, and this is going to be very important. This task, find the equation of a tangent line. We're going to do this many times. So this is one of the most important skills that you actually have to master. So for this particular problem, what is it that we have to do? Well, we have to calculate the derivative because the derivative, f prime, is the slope of the tangent line. It is the instantaneous rate of change. It's the limit of the lines that are not quite tangent, but that would be nearby. And in this case, I want the derivative, the slope of the tangent line, at -3. So this means this tangent line's slope, as opposed to some other tangent line slope that I'm not interested in. Okay, the definition of the derivative, well, we'll use it in the x approaches a form. This would be the limit as x gets close to a, in this case it's -3, of f of x minus f of -3 over x minus -3. All right, you're going to have to learn that definition. It is a difference quotient, delta y over delta x. Right? So now you just substitute in limit as x approaches -3 of f of x is known to be x squared. F of -3 means -3 squared. -3 squared is 9. Divided by x minus -3. Well, I can do that, x plus 3. And we've been in this kind of situation before. You're going to factor. So you get x minus 3, x plus 3. And this time it's the x plus 3's that are going to cancel, which is good because you don't get a 0 over 0 anymore when you're done. So you have the limit as x approaches -3 of x minus 3. And that's an easy -3 minus 3, -6. So this is our slope, which makes some sense if you look at the picture, right? The slope looks like it's steep going down. Okay, so we have our slope. What about a point? Well, if we know that x is -3, then the y we can get by just plugging -3 into our function for f of x. So -3 squared is 9. So the coordinates of this point would be -3, 9. So there's our y value, our point rather, and here's our slope. Whoops, point, slope. And now we need the equation of a line. And I wish that I could convince students that you can write an equation for a line in a very, very simple way if you use the point slope form of the equation of the line, which goes y minus the y value equals the slope times x minus the x value. And folks, right here, you can say you're done. There is no need to take the 9 over to the other side and multiply all this crud out and then come up with an answer that looks like y equals mx plus b. Of course, if somebody asks you for the line in that form, then yeah, you have to do it. But I didn't ask for the line in that form. I just asked for an equation of the line. This, all by itself, is a perfectly good equation or line. Now you might want to rewrite that as x plus 3, but that's not a big deal. I mean, this is correct. Nobody's going to take off any points for you for doing that. If a grader ever takes off points, just come see me. I will give it back. No problem. Okay, so this is the kind of problem that you'll have to do for sure on a test. In this kind of situation, the calculations won't be any more difficult than this, where you've got to do a simple factoring and canceling, or maybe dealing with 1 over x, because that's not too difficult either. You need a common denominator, but certainly not as difficult as the thing that we went through a little while ago. All right, time to do a nasty problem again. So much for an easy one. So let's suppose that we wanted to calculate the derivative of f at a again. This time they're not telling us what a is, but f of x is something nasty like the square root of 1 minus 2x. Well, how do we do that? Well, we write down the definition of what f prime at a means. F prime at a is a limit. It's the derivative, so it's a limit as x gets close to a of f of x minus f of a over x minus a. You should do this like this. Don't skip this step because it helps you remember the definition of the derivative. It's the limit of the difference quotient. So now you just substitute. This is the limit as x goes to a of the square root of 1 minus 2x minus the square root of 1 minus 2a divided by x minus a. You do a quick reality check and find that sure enough, as x gets close to a, 1 minus 2x becomes 1 minus 2a, and you're going to get 0 up top, and you're going to get 0 on the bottom. So this is really a 0 over 0 bad news situation. What are you going to do? Well, the trick here is just multiply by the conjugate to get rid of those radicals, and maybe something good will happen. So the conjugate is going to be this thing plus that thing. So I'm going to multiply top and bottom of this fraction by that radical plus that other radical. Okay. Now, in the interest of time and not taking up too much space here, every time I take an a minus b, which is what I've got here, this is really an a minus b, and I multiply it by an a plus b, I'm going to end up with a squared minus b squared. And the nice thing about that, the reason why multiplying by the conjugate works, is because a squared makes a radical go away, b squared makes the other one go away. Now it costs you, you end up putting something in the denominator, but it'll work out. So this is going to be the limit as x approaches a of, now when I multiply by the conjugate on the top, here's what's going to be left. You're going to be left with a squared, which is 1 minus 2x with no radical, so I'll just put it in parentheses, minus 1 minus 2a with no radical. That's all that's left on top. The bottom is ugly. X minus a times what? Square root of 1 minus 2x plus square root of 1 minus 2a. But if you look carefully on the top here, this 1 minus 2x minus all this minus has to distribute across the 1 and the minus 2a. So you're going to be left with 1 minus 2x, I'll do it on scratch paper here, 1 minus 2x minus 1 minus minus 2a. So I've got the 1 and the minus 1 going away, and I'm left with minus 2x minus plus 2a. Now the neat thing about that is that I can factor out a minus 2 from here, and look what's left. X, now I've got to put a minus here, and the 2 is gone, and I've got a left. So really what's happening is that this x minus a is going to cancel that x minus a when all the dust clears. So this limit becomes nothing more than the limit as x approaches a of minus 2 on top. That's all that's going to be left after you cancel your x minus a. And on the bottom, you've got 1 minus 2x under the radical plus 1 minus 2a under the radical. And here, if you do your reality check, you find something very different. As x gets close to a, the only thing that happens is that x becomes a, but you get a plus here instead of a minus. And that's very good news, because now that's going to give you minus 2 over radical 1 minus 2a plus radical 1 minus j as x approaches a, which gives you 2 of those guys, canceling the 2, leaving you with minus 1 over radical 1 minus 2a. And that, folks, is the derivative. Nasty problem, but it's worth doing from time to time. Okay, not much left now. I just want to talk about a problem that's a little bit silly. These are problems where the book asks you to look at an expression that looks like this. Limit as h goes to 0 of the square root of 9 plus h minus 3 divided by h. And the question is, well, with this difference quotient, or with this expression, this is supposed to be the derivative of some function f at some number a. And so the question that the book is asking here is, what's f and what's a? What is a? And to answer that question, you just look at this expression f prime at a and write out the definition. This is the derivative. Of course, you're going to write the derivative in the h equals going to 0 form. So this is the limit as h goes to 0 of f of a plus h minus f of a all over h. Yeah, you have to have that memorized. There's no way around it. Okay, and then you play the game of pattern matching. What's going to have to be f and what's going to have to be a? Well, how are you going to get this square root function in here? And it's going to have to look like a plus h underneath it. And if you think about that for a minute, it doesn't take too long to figure that f of x is going to have to be the square root of x, because you're not going to get that radical any other way. And looks to me like the a is going to have to be 9, so that when you take f of a here, it's going to be the square root of 9 or 3. So in fact, this is the answer. F of x equals square root of x, a equals 9. And you just plug in and you see that f of a plus h means the square root of a plus h. And once you know that a is 9, that a turns to 9. That's the problem. 9 plus h under the radical minus the square root of 9. Okay, so that was it. Kind of silly. Let me give you a different problem, which is even easier. And here they give you the limit as x approaches 6 of something like log x minus log 6 over x minus 6. Same question, right? What's f? What's a? And then if you think about that, f prime at a, in this case, is going to be a limit as x approaches a. We won't use the h form here, obviously, because x is approaching 6. So as x approaches a of f of x minus f of a over x minus a. And this is even more obvious. What's f got to be? Well, looks to me like f of x, you have no choice, has to be log of x. And a has to be 6 to make the pattern fit, right? So this has to be that. F has to be the log function, and you're done. Okay, one last thing to do, and that is to talk about units. What are the units of f prime? What are the units of the derivative? And the answer to that question is very, very simple, because what is f prime? It's a limit. F prime of a is a limit of something that looks like delta y over something that looks like delta x. So the units, the limit isn't going to change anything here. The units are whatever the units of y are divided by whatever the units of x are. So if you're talking about distance versus time, then your units are going to be like miles per hour. We've seen that kind of thing before, but often we get interesting different problems. We'll see a lot of these kinds of problems. Like suppose that you were talking about cost as a function of or dependent upon length. That happens. Here's an example. Suppose you're putting things on a shelf in a store situation, and you're charged by how much shelf space you're going to take up with your commodity. So your cost depends on how many inches of shelf space you have. So you might find that if you increase your shelf space, you're going to add more money. So you ask the question, what happens? What's the rate of change for this function? And the book asks a few questions in the last few problems that I'm going to ask you to do, and those questions have to do with simply what are the units of such a thing? And the answer, well, whatever the unit of cost are, which would be dollars, and whatever the units of length would be, which would be like inches. So dollars per inch. So if you're here, for instance, you might find that it costs you $20 per inch to make a change, but if you get out to here, it might be only $15 an inch to make a change. We're talking not about how much it really costs, but what is the rate of change of the cost. So that's the question the derivative asks. The question the derivative asks is how fast, or what is the rate of change, and not over the whole period, but right here. If you're thinking of making a small change, what is that going to be? And the units will be in whatever dollars or cents or whatever you're talking about, cost units divided by length units. Okay? It's always whatever the units of y are divided by the unit of x. Okay, I think we've all suffered enough.